Okay, now let's do one example from the gas mixture. In this example, we have a rigid tank with a given volume, which is 1 meter cube, and this tank has two equal sized compartments. Uh, and those compartments are separated from each other with a membrane. In one compartment, we have neon gas at 22 degrees C and 105 kPa, which is the pressure. In another compartment, we have argon gas at 50 degrees C and 195 kPa. Now, the membrane fractures and the two components mix with each other. As the two components are mixing, there is a heat transfer from the tank to the surrounding, like 12 kilojoule of heat is lost from the tank. The question is asking for the final temperature of the mixture. Okay, so let's say this is my tank, and this tank has two equal size compartments, let's say the left and the right side. In one side, I have neon gas at 22 degrees C and also at 105 kPa, which is the pressure. This is all I know. And in the other side, I have argon gas at 50 degrees C at a higher temperature compared to this one and at pressure of 195 kPa. So on the right, both the temperature and pressure are higher than the left side. Now this is the membrane, so let's pretend that is the membrane. So this is before the membrane ruptures. Now the membrane ruptures, these two gases combine with each other and there will be 12 kilojoule of heat to the surrounding, from the tank to the surrounding. Okay, so obviously the entire thing changes, the pressure changes, the temperature changes, and the question is asking for the final temperature, like once this heat transfer is done. So basically, this is a first law problem, the conservation of energy, and I'm going to do the COE here. Energy going into the system minus energy leaving the system is equal to the change of the energy within the system. Okay, now here what I have as the system is this tank, right? And it's a rigid tank, meaning that its volume is constant. No matter how the pressure changes, the volume remains constant throughout the entire process. Now, in this system, there is no energy going into the system. In fact, there is an energy leaving the system during the process, okay? And that process, by the way, starts after the membrane ruptures. So there is energy going out, and that energy is in terms of heat. So what I have is negative Q on the left hand side, because we know that generally speaking on the left hand side of the first law we have either energy transfer by heat or energy transfer by work or energy transfer by mass. Okay, so generally speaking on the left hand side we can have either heat, work, or mass. Okay, so right now there is no work associated with this problem, there is no mass associated with this problem because the entire thing is my system, but instead there is a heat which leaves the system. So that's it, that is all I have on the left hand side. On the right hand side I have the change of internal energy from state 1 to state 2. So the difference of them is going to be U2 minus U1. Okay, and if you realize, I wrote down all these properties in uppercase. So this is uppercase Q, uppercase U, and uppercase U. Now, this U1 is the total internal energy before the membrane breaks, and this is the total internal energy after the membrane breaks and after the heat transfer completes. Okay, so the initial internal energy, the final internal energy. Now, the question is asking for the final temperature. That final temperature is evaluated at U2, or I could say U2 depends on that final temperature. So if I know U2, then I'm able to find the final temperature. Okay, now I'm going to start this problem by solving this equation, because in this equation Q is known I know the value of Q, and that is 12 kilojoule. U1 is not directly given, but with some calculation, I'm able to find U1. So if I solve this problem and if I obtain U2, then based on that U2, I should be able to find the final temperature. So let's do that. First of all, let me find U1 first. That U1 is the total internal energy before the membrane breaks, which is equal to the sum of mass of each component multiplied by internal energy of each component. So the unit here is kilojoule. The unit here is kilojoule per kilogram, so that's why we are multiplying that by kilogram. And that will be mass of neon gas multiplied by U of neon gas plus mass of argon, U of argon. Okay, so in order to find U1, capital U1, I need to have the masses. So I need to find those masses first. And that is doable. I can apply the ideal gas law to obtain the mass of each component. So let's do that. The ideal gas law says PV is equal to RT. So P is the pressure, V is the specific volume, R is the gas constant, and T is the temperature. Okay, I'm applying this law to both of these two sides, but separately. So let's first apply that to neon part. Okay, so that means I need to consider the pressure of neon, which is 105 kPa. The specific volume of neon, that I don't know, but I'm looking for that, because if I know the specific volume and because I know the volume of each side, then based on those two I can find the mass. And by the way, regarding the volume, I know the total volume is 1 meter cube, so that means this portion of the tank is 0.5 meter cube, and also this portion of the tank is 0.5 meter cube. So that's why I'm looking for the specific volume, because by having the volume and specific volume, I'm able to find the mass. Okay, R is going to be R value for the neon gas, so that comes from the table A1, and for neon is 0.4119 kilojoule per kilogram Kelvin, and T here is the temperature of neon gas, but I need to convert that into Kelvin, so I need to convert 22 degrees C into Kelvin, and that will be 295 Kelvin. Okay, so by solving this problem, I'm able to find the specific volume for neon gas before the membrane breaks, and that is 1.15 meter cube per kilogram. Okay, now that I have that specific volume, I can obtain mass of neon gas at the very beginning, and that is going to be the volume of the compartment, the left compartment over the specific volume of the neon gas. So the volume of the left side is 0.5 meter cube, the specific volume is 1.15 meter cube per kilogram, and that gives me mass of neon gas equal to 0.432 kilogram. So this is how much neon I have at the very beginning. So let me just write it down. So M of neon gas is 0.432 kilogram. Okay, now let's do exactly the same thing to the argon gas as well. Okay, so that means I would say pressure of argon multiplied by the specific volume of argon is equal to RT, the temperature of argon. Okay, so pressure of argon is 195 kPa. The specific volume is unknown, that's what I'm trying to find. R is 0.2081 kilojoule per kilogram Kelvin, and T is going to be this temperature, but after converting to Kelvin, all right, and that will be 323 Kelvin. Be careful with the unit for temperature. And that gives me the specific volume for argon gas equal to 0.344 meter cube per kilogram. Okay, now by having that specific volume, and because I know the volume of argon gas, I can find mass for argon gas, and that is equal to the volume over the specific volume of argon gas. So volume is equal to 0.5 meter cube, and a specific volume is 0.344 meter cube per kilogram, and that gives me mass of argon equal to 1.45 kilogram. So that means here, before the membrane breaks, I have mass of argon equal to 1.45 kilogram. Okay, so once again, my goal at this time is to obtain U1, because if I have U1, and since the value of Q is given in the problem, then I can find U2. And by having U2, which is the internal energy at the end of the process, I'm able to obtain the final temperature that the question is asking for. Okay, so in order to find U1, I also need to find the internal energy of each of the components. So let's say U1, this is lowercase u1 for the neon gas is equal to CV, or specific volume at constant, specific heat at constant volume, multiplied by T, temperature, okay? And that is going to be CV for neon gas is equal to 0.6179 kilojoule per kilogram Kelvin, multiplied by the temperature of neon gas is 295 Kelvin, and that gives me U1 for neon gas equal to 182.2 kilojoule per kilogram. Okay, now in case you're asking where did I find this comes from table A2. Okay, table A2, and that is CV for neon gas. Now I also find the internal energy in state 1, meaning before the membrane breaks, but this time for argon, and that is CV, or the specific heat at constant volume for argon, multiplied by its temperature. So the specific heat is equal to 0.3122 kilojoule per kilogram Kelvin, multiplied by the temperature of the argon gas, and that gives me the specific internal energy at state 1 for argon gas equal to 100.8 kilojoule per kilogram. Okay, now that I have these lowercase u values, and because I also have the mass of each gas, I can find uppercase U1. So uppercase U1 is, I'm using this equation, is mass of neon multiplied by U of neon plus mass of argon, U of argon. Okay, so capital U1 is equal to 0.432 kilogram multiplied by 182.2 kilojoule per kilogram plus 1.45 kilogram multiplied by 100.8 kilojoule per kilogram. And that gives me uppercase U1 equal to 224.8 kilojoule. Okay, so this is in fact the total internal energy before the membrane breaks. Now I need to find U2 so that I can find temperature. In order to find U2, I'm going to use this correlation. So based on that, I can find U2, and if I have U2, I can find the temperature. So let's do that. Actually, I can still use this space. So if I call this equation 1 star, so if I call this, then I'm going to use that equation. So the equation 1 star gives me negative 12 kilojoule is equal to U2 minus uppercase U1, which is 224.8 kilojoule. Okay, and that gives me U2 equal to 212.8 kilojoule. So this U2 is the total internal energy after the membrane breaks and after the heat transfer completes. Okay, because we had 12 kilojoule of heat transfer to the surrounding. Now, this U2 for me is equal to the specific heat at constant volume for the mixture multiplied by the temperature of the mixture and also by mass of the mixture. Okay, the reason is the product of these two gives me U2 of the mixture, but this U is lowercase. That means the unit here is going to be kilojoule per kilogram. If I want to find uppercase U2, which the unit is in kilojoule, similar to here, then I need to multiply that by the mass of mixture. So this mm is mass of mixture. Okay? I know what the mass of mixture is because I know the mass of each component, and the mass of each mixture is simply sum of those two. So this part is easy. The temperature of the mixture is what I'm looking for. So that is the unknown. That is the question mark. The left-hand side is also known. I have the value of U2. All I need to obtain in order to be able to solve this problem for Tm is the CV value for the mixture. Okay, so finding the CV value for the mixture is the very last step that I need to do. So that's my goal. I want to find the specific heat for the mixture. In order to find that, in order to find CV for the mixture, I'm going to use the equation of that CV is equal to mass fraction of each component multiplied by CV of each component. Okay, so mass fraction is the fraction between the mass of each component to the total mass. I know the mass of each component, so I'm able to find this MF or mass fraction. So that is going to be mass of neon gas was 0.432 kilogram over total mass, which is the mass of both gases combined together, which is 1.882 kilogram, multiplied by CV for neon gas, that is 0.6179 kilojoule per kilogram Kelvin, plus, now I do the mass fraction for argon, that is 1.45 kilogram over 1.882 kilogram multiplied by CV for argon, which is 0.3122 kilojoule per kilogram Kelvin. Okay, that gives me CV for the mixture equal to 0.382 kilojoule per kilogram Kelvin. Okay, so this is in fact mass fraction for neon gas, and this is in fact mass fraction for argon gas, MF argon. Okay, this is also CV for neon gas, and this is CV for argon gas. Okay, now that I have this CV for the mixture, I can go back to this correlation. So let's say U2 is known, is equal to this much. CV, I just obtained the CV for the mixture. I know mass of mixture, which is pretty much what I used here, 1.882. So based on that, I'm able to solve for Tm. Okay, so I'm using U2 equal to CV of mixture multiplied by the temperature of the mixture multiplied by mass of the mixture. So U2 is 212.8 kilojoule, which is equal to CV of the mixture 0.432 0.382 kilojoule per kilogram Kelvin, multiplied by Tm, the temperature of the mixture, multiplied by the mass of mixture, 1.882 kilogram. And that gives me the temperature of the mixture equal to 295.9 Kelvin, which is equal to 23 degrees C. So this is answer for this problem. Now, although this is the answer to the question and that's enough, but I would like to go one step further, and that is to obtain the final pressure of the mixture. So the question is not really asking about the pressure, but what if the question was also asking for the pressure? So basically the second part of this problem is P of mixture. What is the pressure of the mixture? Okay, so in order to obtain the pressure of the mixture, I'm going to use the equation of the ideal gas law, the equation of state, which says pressure multiplied by a specific volume is equal to RT. R is R of the mixture and T is the temperature of the mixture. So once again, this is pressure of the mixture. This is a specific volume for the entire tank. Rm is the gas constant of the mixture and Tm is the temperature of the mixture. So here, this Pm is question mark. We already found this in the previous step, that is 295.9 Kelvin. So we have that. V is the specific volume of the mixture, meaning that this is the total volume of the mixture divided by the mass of the two components. So this, we already have it. And the only thing that I need to obtain here in order to be able to calculate for Pm is Rm, the gas constant for the mixture. Okay, so that Rm, we had an equation for that, but that Rm is equal to Ru, the universal gas constant, over Mm. Capital M is the molar mass, right? The Mm, or the molar mass of the mixture itself, can be obtained based on these correlations. So Mm is equal to mass of mixture over the number of moles in the mixture. Okay, now the number of moles, this is something I need to find. I already have mm, so this m is subscript of this one. This is mass of mixture, and I have it, okay, because I have the mass of each component and some of them is my mass of mixture. So all I need to find is the number of moles in each of the species. So the number of moles in neon gas, so number of moles in neon gas is going to be equal to mass of neon, okay, over the molar mass of neon. So mass of neon, we obtained that 0.432 kilogram, and the molar mass for that is 20.183 kilogram per kilomole. So this number says each 1 kilomole of this gas, neon gas, has 20.18 kilogram of mass. And if I do the calculation, it gives me the number of moles equal to 0.0214 kilomole. So this is the number of kilomole neon we have in this tank. I do the same thing for argon. So the number of moles in argon is equal to the mass of argon gas over the molar mass for argon. So mass of argon, I obtained that 1.45 kilogram, and the molar mass for that is 39.94 kilogram per kilomole, and that will be equal to 0.0362 kilomole. Okay, now by adding these two numbers together, that I can find Nm, the number of moles in the mixture. So the number of moles become 0.0576 kilomole. This is the total number of moles I have in the mixture. So that number comes into here. This is my Nm. Okay, so my denominator is 0.0576 kilomole, and my mass of mixture is in fact 1.882 kilogram. Okay, so that gives me the molar mass of 32.6 kilogram per kilomole. Okay, now this mm comes into here, so basically this equation goes on top, and here I will have 32.6 kilogram per kilomole, and for Ru here I will have 8.314 kilojoule per kilogram, kilojoule per kilomole Kelvin. Okay, so that gives me Rm of 0.2544 kilojoule per kilogram Kelvin. So this is the gas constant of the mixture. Okay, so this is this Rm that I have. So this goes up, and then I can solve for Pm. And the Pm is going to be equal to 141.6 kPa.